Okay, so by the way, if you have any questions or any doubt, you can ask on the WhatsApp or you can try to meet me also. So we were looking at overview of DNA computing. And as I mentioned, the last class, we talked about algorithmic self-assembly. So Eric Winfree, uh, who is, who has written the first PhD thesis in DNA computing area. So he took the Wang tile business hardware from Net lab and the idea of DNA computing from Edelman. So finally, I think we talked about these tiles and we were looking at some of the calculations. So let me show you a few things. Okay, we were looking at this binary counter. So you know that in order to construct this binary array, which is binary expansion of numbers 0, 1, 2, 3, 4, 5, and so on, and it's unbounded. So I gave you the solution, but the question is how to find this solution. So any idea? By looking at an array, how do you find the solution? That there are 4 tiles which can actually give rise the whole stuff. Any idea? I want to listen any of you. If you have attended last class, so I gave you the solution. Okay, these 4 tiles are going to work, and obviously this input and output is these Boolean functions OR and AND. So the question is, you see, I should tell you what we should do. Look at the array carefully, okay, and then look at the distinct information flow in the face value of the tile. So basically, if you look at, for example, this tile here is 0, right? So face value is either 0 or 1, right? So you try to find the information flow and see you can find if you can find a basic tile which is giving you that information flow. So that's how you separate out basically different computational tiles from the array. Okay, so obviously one of this style is this, right? So the information flow capturing will require some practice, of course. So suppose you are taking a final year exam, the final exam, and I ask you, there is a pattern, find the tile set. How many will you be able to do it? By the way, in the previous time, once I taught this DNA computing, people were able to solve this problem. So it requires practice, right? So it's not a difficult problem, but yeah, how do we find? So it's kind of a challenging thing. So how do you find the information flow? So as for this binary counter, now this, as I mentioned, so in these computational ties, we can describe. There is no need, but it's a handy tool if we describe 2 input, 2 output. So as a Boolean function, right? So output is a Boolean function of input, right? So that thing give rise to what is known as computational tile. So this is a general definition of computational tile. There are 2 input, 2 output, and face value is whatever is on that output is the face value of the tile. Okay, so this is the. So basically, if I have to given a pattern, I have to find tile set for that. So in that case, I need to somehow find out these functions so that I know these values. U prime, V, U, and V prime. Once I know these values, and actually the role of the function stops here. Once I know these values, means I know the assignment of colors at each edge. and our job is done. Okay, so this assignment of color is important. Okay. So luckily, or here we can express this assignment of colors in the form of functions. So it's easy to describe the tile set. Okay, so let me show you a few more examples. Now actually, you see, I can further change it. Same binary counter. Now you see how many tiles are there? 8 computational tiles are there. So 1, 2, 3, 4, 5, 6, 7, 8. And how many colors are there? 4 colors, 0, 0, 0, 1, 1, 0, 1, 1. Right? So this will also give you the the binary counter pattern. Okay. But now number of frame tiles are more. There were 1 seat, 2 frame, 1 vertical, 1 horizontal. Now we have 1 seat, 1 horizontal, and 2 vertical frames. So this has increased, right? So number of frame tiles increased, and obviously now the question is, what will be the scenario of function that we were talking about? So now it is no more. There are 2 bits going, 2 bits going. So how many bits? By the way, how many bits? By the way, I should ask. There are 8 tiles. So how many bits are possible? Input bits are possible. No. 3. 8 tiles are there, right? Total 8 tiles are there, right? So 3. So out of this, I have to assign 3 inputs and rest of them are output. So I need to find a function which will describe this. Okay, and this is a challenging problem. In fact, I have discovered one tile set. There was an open problem which I solved, and you will see that actually finding this function is still difficult thing. So if you can do it, if somebody wants to do it, they can contact me, right? So it will be a nice thing if you can find the function which is describing the whole system. Okay, so why do we do this actually? So when you actually grow this on the simulation or in the reality, you observe that a lot of errors will happen, and the errors are different kind. Mismatch error. Why error happens? Because hybridization may not be perfect. So what happens? 0 color should match to 0 color. 1 color should match to 1 color. But what happens? 0 color will partially mismatch to 1 color because 0 and 1 colors corresponds to DNA strands, right? So they may not be completely hybridized thing, but partially bits may match A and T and C and G. So what will happen? 0 and 1 color will also match. So there will be a mismatch error. And so if there is one error, obviously there will be more errors. The whole configuration will be blown up, right? So this is a difficulty. So this is a very clever scheme discovered by Peng Yin, who is now at Harvard University, professor at Harvard. So I know him when he was doing PhD at Duke. So he has in his thesis actually he created these things. So basically, when you blow the bits, so basically what is happening? Normally, if you know, in the error correcting codes, as you know, if you want to protect the information, you repeat, introduce redundancy into the system. Rather sending 0 or 1, you send 0, 0, 0, 1, 1, 1, right? So that you can correct 1 bit flip. So here also, we are introducing redundancy in the system through this. So we are blowing the bits, okay? So obviously number of tiles will be more. More resources will be required, but errors will slow down. Okay, so this is the key idea about this blowing the business. And in fact, they constructed this 4 and then they posed an open problem. Can you do it with more colors? 8 colors or 16 colors. So we solved it for any power of 2 actually. I will show you that solution briefly. May not be in general, but yes. Here is the 8 color solution that I gave actually with my collaborator Naveen Kashyap. So this is, you see, same binary counter. Now there are how many colors? 8 colors. So how many inputs should be there? Number of tiles are how many? 16 to 4 inputs. So easy exercise for you or t time problem. Can you find that function which I was talking about? Yeah, so 4 input, rest could be output, right? So now you kind of find this function. Now the function is kind of a Boolean function related to bitwise, how this will work. That is something interesting exercise, right? I have not stopped. Even I went a bit further. So for any power of 2 color, we have given the construction in 2006, and there was another construction by Eric Winfree himself. So this is again using our method. Now there are how many tiles? You can see that. How many tiles are there? You can count. 32, right? Yeah. So 5 input and so on. So question is, if you have a given problem, means a pattern, and if I ask you find functions which can describe the computational ties, your job is done, right? So rest of things are straightforward. So that is a challenge. How do we find functions which can describe the computational ties? But you can see that same binary counter, we are able to solve it with 4 tiles. We are able to provide 8 tiles solution. We are able to provide 16 tiles, 32 tiles, any power of 2. Right. So that is so question is, obviously you want to minimize the number of tiles used because it will use less resources. And also you want to basically minimize the error. But then there is a trade-off. If you introduce redundancy, tile set will increase. So what is the best way? That is a interesting problem to look at, right? So I think I am not showing. Now, the question is for this, what are the functions at least? Yes. No, the number of tiles are changing, right? So,
two inputs. Yes, in 4 tiles we have 2 inputs. So can we just give the 2 inputs in repeated form? For example, we can repeat the 2 inputs 3 times. So we will have 6 inputs. But then we have to find some function that the number of tiles.
Yeah, we need to find if there is any function which will work. Because in terms of logic, what happens, as long as you remember the tile assembly model, colors should match. So I have to somehow find these colors, or in terms of these bits, right? That you can do. So that's what we are doing in the previous one, right? You see there are 4 bits, right? Yes. Think about it and discuss and see if you can come up with something. So you tell me. So the thing is that there is another scheme which I have not told you, where Winfree has blown the tiles itself. So one tile, he has actually what he has done. He has the north bit, south bit, east bit, and west bit. You just copy. So each one tile you replace with a tile system of 2 by 2, 4 tiles, and the internal tiles are internally connected, and their upper edges are so the upper edge will have north twice repeated, east twice repeated. Okay, so that mechanism also slows down the error rate. Yeah, but the only problem is that it is your structure you wanted to create up to this much, it is taking more. Right. So that is a problem. So all kind of interesting things are there actually. No, here, what is the function? At least you can tell me the Boolean function here. Anyone in the class? What function is used here? This is easy actually. So there are 4 computational tiles. 2 inputs, right? So 0, 0, 0, 1, 1, 1, 1, 0. These are the 4 possibilities of inputs. And those are the outputs. What are the Boolean functions? XOR. Both of them are XOR actually. You see? So it's the easy thing. So one is XOR, one is AND, you get binary counter. Both are XOR, you get Sierpiński triangle or Pascal triangle mod 2, or the Indian name I forgot actually, by the way. So that is something interesting, right? So question is, any mathematical problem, if you want to solve with this tile system, you have to provide these functions. Then it is easy, or otherwise you provide directly tile set, you know. There are students in your class, I mean, previous years, who have actually, actually computed different kind of tile set for solving different kind of problems. So they can do this programming easily. So, you know, this is the X-style front end. Although right now there is an issue with that system. So here you see we have given this, what this program used to do. You choose A and B, and you know, you choose the function, and it will give you the dot tile file that I have shown you, so that you can simulate it directly. You know. So I still remember when we did this. So basically, we did this in a more general way. Then with Eric Winfree at Caltech, he has to actually change his simulator based on our work. You know, so this was really interesting at that point of time, but it's quite old now. So there is a standalone version of this Xtile 3.0, which is available. If some of you want to do some contribution there, it's already written. Some patching and some, obviously you need to understand the whole code, right? Understand the logic, which will take at least 1 week or 2 weeks, depending upon your Shraddha, right? And then you can contribute. So contribution point of view, it's not much required, but you need to understand the whole thing. So these were the students, you know, Anshul Chaurasia, Pratik Jain, and Sudhanshu Devedi. So they went it to present it F Nano conference in 2009, supported by Microsoft Research, by the way. So you can download Xtile. Here is actual simulation of Sierpiński triangle in the real experiments. Once you design the tile set, you design the molecules, right? These DNA molecules, and then they are doing the, you know, actually you see the pattern is observed. At the, I think there are a couple of more pictures here I can show you. And it is clearly visible that errors are there actually, right? So how to control it? So they have actually shown how to control the errors also, you know, without error correction and with error correction. These are some of the images. This paper you can read if you want to know about Sierpiński triangle. This is a tile set for addition. Addition of two numbers. Now, who can understand this? Of course, input is in the form of bits. Two numbers, corresponding bits you take, right? Now, those 8 tiles, this method is a little bit different. So till now I have told you about two-dimensional array formation, right? This is single dimension. So what happens here? These 8 computational tiles, you can write, this is the general formula for all of those 8 tiles, right? Okay, so these 8 computational tiles can add any two numbers. So if A is this 1001, B is 1010, of course addition is this. So this is a seed. So seed frame. So here is 0, right? So sorry, 1010. The second one B. Here it is A, right? So 1001. So these are the two inputs here. This is the seed and the whole frame. And now those computational tiles from eight possibilities will come and try to fit it and grow it. As you can see, that output is written in the middle. Okay, so when you do this addition with two-dimensional, so you can get output written at the top. Once the computation is done, you can write output in the diagonal if you want. Okay, you can write output on the right side. That is your way of doing this stuff, you know. Any place you can write the output. That depends on how do you design the computational tile set. Any question at this point? Okay, so you see here is a RAM circuit self-assembly with the tiles. By the way, there is one PhD thesis, and now after that there is a book also on DNA self-assembly based processor. So this is the best processor ever created. And the person Chris Doyer, who did this at Duke University, he is now working on the classified project with the government, United States government, right? So because it's an important one. That book is available in the library if you want to read how to design processor based on DNA self-assembly. Okay, so at one point of time, I gave one student. You might have heard about FPGA, right? Anybody heard about FPGA? No, other than CP, nothing. So anyway, FPGA is a very important thing. Field programmable gate array. So basically, in FPGA, can you build FPGA with the DNA self-assembly? It's an interesting task. I gave it to him, but I think he could not complete it. But anyway, that is something, a possibility. Now I'm going to talk about certain thermodynamic stuff because even in the construction of DNA codes, I talked about melting temperature and other constraints. So what are these things? I'll just familiarize these things. I'll tell you about. So this is our. So we have this forward rate of reaction, backward rate of reaction. So essentially, each DNA molecule. So you can, of course, there will be some concentration of each DNA molecule, right? So you can write differential equations, kind of thing, right? So probably you might have studied in your JE course or something. I don't know where. Have you studied chemistry, right? Somewhere. Thermodynamics is very important, by the way. Can anyone tell me? So I told you that in models of computation, there are 4 kind of machines possible, right? Finite automata, push-down automata, linear bounded automata, and Turing machine. In terms of classification, very important summary of computer science, right? If I want to classify machines thermodynamically, how many machines are possible? And in fact, there are interesting questions. What is the thermodynamic cost of doing computation? Okay. So there is another very nice branch which has come up known as green computing, right? Or green linear algebra. Linear algebra which reduces the carbon footprint, right? It's a green linear algebra. Or low power linear algebra. I think you might have heard these terms somewhere. It's very innovative or way to look at. So for a task you can do in one way. That algorithm has certain thermodynamic cost or certain carbon footprint cost. Another algorithm which may be better. So you need to find an algorithm which is better in terms of doing reducing carbon footprints and thermodynamic cost. So basically, by the way, at each of these big companies, Google, Facebook, they have director for green computing. So they look at how to reduce all these things. It's a very important aspect of computer science. I think we don't have any course on that here, but that's very interesting. So this is a T problem for you. How many machines are possible thermodynamically? Google पे ढूंढना तो शायद. Let me see. I don't know. Find. Okay, so now we are going to tell you about Watson Crick base pair nearest neighbor model. This is very important. So when we look at thermodynamics of DNA, because here everything is DNA or ACGT. So there is a popular table that people use. This is the table. Nearest neighborhood thermodynamic parameters of DNA. So pair is AATT. So these quantities delta H, delta S, delta G. Anyone remember what are these things from chemistry? One of them is entropy. One of them is Gibbs free energy. Another one, maybe. So all those things are given there in terms of symbols, right? And their values are given. This is a standard table for the nearest neighborhood of ACGT. Okay, so let me describe these quantities again. Recall what is delta H, what is delta S, and what is delta G, and how to compute, because this is very, very important. By the way, I am not such an expert that how to get these values. I cannot get these values, right? This is all people who are really doing those kind of stuff, By the way, the basic quantity gives free energy, delta G. So this is the potential of a reaction to occur spontaneously, right? Okay, so this is delta G. Enthalpy, the amount of heat released from or absorbed by the system, is enthalpy. Entropy measures the randomness or disorder of a system, and there is a relationship between them. By the way, do you know that your social network, look at Twitter or Facebook, Instagram, what else you use, LinkedIn, whatever. So these social networks behavior you can describe in terms of these quantities. Do you know that? So there is a nice. So basically, what happens? User is adding to the system, right? Each user you can think of a tile kind of thing, right? Attaching to the whole system. Or कुछ लोग छोड़ते भी हैं. Some people leave. So there is a forward rate of reaction, backward rate of reaction, right? And so you can describe these systems nicely with the help of chemistry, actually, which will throw a light more interesting, Anyway, so that is something. So entropy is very, very important thing, right? Measures the randomness or disorder of a system. I think you might have studied these things somewhere. Okay, so now if I want to compute Gibbs energy for this example, CGTTGA and GCAACT. So Gibbs energy is total for initiation plus symmetry plus stat plus terminal, right? So basically, from that table we can compute. So basically, we can form these things. So CG, GC, then GT, CA. Like that, pairwise we can take, and finally we take the terminal thing. We actually compute from the previous table the value of the Gibbs energy, right? All these calculations you can do. Melting temperature. This is very important. The temperature at which half of the strands in a solution are complementary base paired and half are not. Okay, so melting temperature formula is this. R is a gas constant. IT JEE preparation, you remember anything in the coaching? Probably they might have taught it, right? In IT JEE, these things? No. Yeah, CP anyway. So anyway, so also there is a term X, which is 4 for non-self complementary strands and 1 for self complementary strands. Depending upon the strand which you are taking, we can actually compute these things. Melting temperature, very, very important parameter. So here is a calculation for melting temperature. So I think all these values we can, substitute and compute the value, Chemical kinetics, as I mentioned, entire chemistry is a computer science, right? And computer science can learn from chemistry. Your social network, I gave you an example. So basically, things are very, very connected. So now, if I want to do any computation with bunch of chemical reactions, they can always you can always reduce them to certain basic chemical reactions. And what are the basic chemical reactions? Unimolar, right? So unimolar means basically one molecule is disintegrating into certain other molecules, right? Or by one, like 2 combining giving you 3. All others you can build from this. So basically, in general, we have. So suppose we have L ingredients and M outputs, right? And there is some rate of reaction. So we know the rate is this formula you might have, you might be remembering this, right? K times. But did you ever ask your JEE coaching people how to get this formula? What is the reason? No. Just memorize it and use it, right? So I can also do the same thing. Otherwise, I always ask you to ask why, how. That question is very, very important. Curiosity is very, very important. Anyway, so here the forward rate of reaction is given as K times e raised to power minus EA divided by R into T. K is the frequency collision factor, T is the reaction temperature, and R is the gas constant, EA is the activation energy. This is the total formula. So that forward rate of reaction that we are talking about in terms of time is actually, we can describe like this. I will show you the formula now. So this is the general thing, most general thing, right? So reaction is L inputs and M output in the reaction, right? And order of reaction is some of these. In the deterministic, so for example, if rate of change, deterministic chemical kinetics is function of the concentration of the all ingredients. So basically, this is one example. It's kind of coupled reaction, right? X and Y1 will give you 2 times Y1 and so on. By the way, if you really want to see how chemical reactions can solve any computational problems, you can see some of my lectures from natural computing where how to add two numbers, multiply, take fast Fourier transform using chemical reactions. You can build everything through chemical reactions. Okay, so it's very, very new. So you should know a certification program in how to program chemical reactions, right, to achieve the desired output. Anyway, so obviously this will give you this kind of set of reactions, right? This is the basic thing. Now you can solve it in MATLAB if you want, or if somebody teach you properly calculus, so you can actually solve it otherwise also, right? Or otherwise you will use MATLAB anyway, whatever is the way. So for example, in the simple case, if X is converting into Y with rate of reaction K, so the rate of change of X is minus K times concentration of X, right? And you can solve this differential equation to get X0 times e raised to minus KT, right? By the way, whenever we talk about differential equations, so they are very important, right? Describing. Have you heard of fractional differential equations? Not partial, fractional. So you have you know differentiation, right? Like first order differentiation dy by dx, second order d2y by dx2, third order d3y by dx3. What if I ask you differentiate half times, d half of dx half of something? That is fraction. Or alpha times, alpha is a real number. Differentiating something alpha times. Okay? Those are interesting things are there already, known as fractional calculus. And they describe the world in much more better way than your normal integer order calculus, right? I call it whatever you might have encountered, right? So this fractional differentiation is really interesting. So, so this, yeah, fractional differential equations are also. Okay, so now you see, when we are looking at ties, basically we are looking at free sticky ends, right? So each sticky end is single strand DNA. So that's why it is written as SS, single strand DNA1 plus single strand DNA2 with forward rate of reaction, double stranded DNA. Single stranded DNA, combining give you double stranded DNA. This is what is happening at each connection of the ties, right? So in terms of rate, I mean, of course, the equation you can describe in terms of this. And then, so basically, this is our KF, forward rate of reaction, actual formula, and reverse rate of reaction. All these calculations. And these are very sensitive to the oligo length size of the strand. Okay, delta G is the free energy, the free energy released. Okay, so this is the actual formula. So I told you about abstract tile assembly model, which is an approximation for DNA self-assembly process, so that you can do the DNA computation. There is also thermodynamic model based on this. Of course, I am not describing in more detail, but when you do the simulation, you can actually see those things later on. So DNA annealing kinetics, this is the equilibrium constant. Okay, this much portion is enough. Now I will briefly end the lecture by giving you one or two examples of DNA cryptography, which was there. So after this DNA computing thing was done by Edelman in 1994, immediately Richard Lipton, and there were a couple of other people who jumped. Okay, so new computing model, maybe cryptography is in danger zone. Let us show that, right? And so they took what was popular at that time, DES, right? They took the DES and they have actually cracked the DES, with these computing methods, So actually, and you know that in 2001, DES is replaced with the AES. If you remember cryptography class from last year. So most of this lecture and the next lecture will be based on this paper by John Rife Group, DNA-based cryptography. So if you really want to learn or understand, I mean, this is also I'm telling you for your project purpose as well. If you want to read, show me your brain and understand, So that is this paper, okay? So this is your DES. If you remember, there are certain round functions. It's based on Fistel network. If you remember anything, or totally washed off, right? With CP. So anyway, so this is the DES function. There are certain round function, initial permutation, and there is a key generation mechanism also, if you remember, right? So the first attack was there in 1995. Dan is, by the way, professor at Stanford teaching cryptography. So there is a much better course than what I taught. So you can look at Stanford homepage, right? Anyway, so Lipton and these people actually they used so this paper they actually they have shown you see that so they describe a library of operations which are useful when working with a molecular computer. So we estimate that given in one arbitrary plain text and ciphertext pair, one can recover the DES key in about 4 months of work. 4 months of work. Experimentally doing everything, right? Furthermore, we show that under chosen plain text attack, it is possible to recover the DES key in 1 day using some pre-processing. Our method can be generalized to break any crypto system which uses keys of length less than 64 bits. You see, this is the interesting thing that they have done, right? All experimentally done, This is something you should know test tube business as well. Next attack was in 1996 by Edelman, Paul Rotman, Eric Winfree, and Sam. Edelman, as you know, is now father of DNA computing, we can call him. Paul Rotman is a very interesting person. So he invented DNA origami. Last time I met him in 2005 again, yeah. So, he has done tremendous interesting work actually. And Eric Winfree, as you know, is the first PhD thesis in DNA computing. So they have written this paper. So I will read this. Recently, in the previous paper, they described the potential use of molecular computation in attacking the DES. Here, we provide a description of such an attack using the sticker model of computation. So actually, in the DNA computation, whatever I have described you is an autonomous model. Autonomous model means everything is automatic, right? Kind of thing. In non-autonomous model, there are filtering methods and purely experimental approach, doing a lot of test tube work, manual work to do the computations. That is also there. A lot of literature is there in that area, but I think people don't look at much because it involves a lot of manual work, right? It should be automatic, right? So here it is more automated. That's why we cover this, okay? So in this, our analysis suggests that such an attack might be mounted on a tabletop machine using approximately 1 gram of DNA and might succeed even in the presence of a large number of errors. So this was an interesting attack on DES, right? 2 attacks. Now, third one I am going to describe in detail using this style business in my next class. Okay. So I think, do I have anything else here? Yeah, there was another, the same time in 1999, DNA stenography system was developed by these people. So there, So secretly tag the input DNA. Original plain text is not encrypted. So basically, they are, you are describing, you are taking plain text and putting it somewhere in the DNA. Okay, and then actually, basically, you are mix it with the collection of other DNA. But this can be broken. That was shown by John Rife group. So that paper I will talk about in the next one, right? So I think that is the main one. Then I will talk about a couple of other developments in the DNA cryptography. Okay, and then we'll go to the DNA origami cryptography, which is another very interesting thing. So I hope you have got enough things to work on. Any questions? No questions, right? By the way, maybe can you give me signature of all the people who are here? Somebody can count?